Alright, so in this video we're going to cover the alternating series test and also absolute convergence, absolute versus conditional convergence, which are a couple of terms that only apply to alternating series. And then finally we'll get to the remainder of alternating series, or the error, which is a very specific type of problem they sometimes ask about these. It's very simple, but the main topic here is alternating series, and then whether it's absolute or conditional convergence. So what is an alternating series? Well, it's just a series that goes plus minus plus minus. So all the series we've looked at so far, like the harmonic series, would be 1 plus 1 half plus 1/3 plus 1/4. But you'll notice that in this one we've got a -1 to the n. So what's that going to do? Well, a -1 raised to an odd power is going to be a -1, but a -1 raised to even powers is a +1. So that's how you get the plus minus plus minus. So this formula right here, it's a harmonic series because it has just n to the 1 downstairs, but it ends up being 1, actually that'd be a -1 as I've drawn it because we start with -1 to the first, so that'd be -1 plus 1 half minus 1/3 plus 1/4 dot dot dot. And then if you're like, oh really, I'd rather see the harmonic series, alternating harmonic series with a +1 out front, if we just throw a -1 onto the n right there, then that'll sort of switch the signs, and we'll get 1 minus 1 half plus 1/3 minus 1/4. So if you're ever trying to cook up a formula for an alternating series and you're just off by 1 with the pluses and minuses, just throw a -1 or a +1 on that exponent -1, and that'll just flip all the signs to the opposite of what they were before. Alright, so it turns out the big trick on these is that they pretty much always converge. And that is really good news, right? So since we've been studying all these different ways to figure out if a series converges or not, because it's kind of tricky, with alternating series they always converge. So even though the regular harmonic series diverges, the alternating harmonic series converges. And it turns out the only time that alternating series don't converge is if their terms don't approach 0. So if you look at something like this one, it's alternating, but 1 minus 1 plus 1 minus 1 plus 1, you can see if you sort of kept a running total, you start with 1, then you take away 1, so now we're down to 0, but then we add 1, so we're up to 1, but then we take away 1, so we're back to 0. So this sum, as you keep adding one more term, you keep bumping up from 1 to 0 to 1 to 0 to 1 to 0 to 1 to 0. And that's kind of like a limit. Just like a limit problem would not have a limit if you're just alternating back and forth. Like the limit is theta approaches infinity of sine of theta. Sine theta just keeps going up and down from -1 to 1, -1 to 1, -1 to 1. So that does not have a limit. And same thing here. Even though it's a finite number, this thing isn't going to infinity, but it is jumping back and forth between 1 and -1 the whole time. So alternating series converge pretty much no matter what, as long as the nth term is approaching 0. So basically this only has to satisfy the nth term test of the limit as n approaches infinity of a sub n needs to be 0. But aside from that, alternating series all converge, whether they're harmonic, p series, p series, all the stuff that would have failed before, like if it would have failed the ratio test, or if it would have failed the p-series test because p was less than 1, that's fine. If it's a geometric series, actually the ratio would still have to be less than 1 because it's got to be approaching 0, but anyway. So that's, if the question is what converges, they all converge, essentially. If it looks like it might converge, it probably does. Then there's this question of absolute convergence versus conditional convergence. And all that's saying is, if we look at this thing, this is the alternating harmonic series again. So it's just the harmonic series except with minus plus, minus plus. We know that converges. Because by the alternating series test, which is just that the terms are getting smaller and smaller, and we have plus minus plus minus, we know that thing converges now. But does it converge absolutely? So when they say absolute, what they mean is absolute value. So that's saying, hey, you know what? If we took this sequence and took the absolute value of it, so basically turned all the negatives positive, so that all the terms were added to each other and none of the subtraction business, would it still converge? Or does it only converge if you have the minus signs thrown in there? So if you took the absolute value and it still converges, then it would be absolutely, it would converge absolutely. So for example, this one down here, this would converge, because it's alternating and the terms get smaller, it converges conditionally. But it also it converges absolutely, because even if we switched all these to plus signs, this is a p series, or it's a geometric series, 1/2 to the n, or 1 over 2 to the n, however you feel like writing it. And because that ratio is 1/2, which is less than 1, this thing is a geometric series that converges, even if it is all plus signs. So this one converges absolutely. But then this top one, if we took the absolute value of it and replaced all these negative signs with plus signs, all of a sudden it diverges, right? Because then it's just a regular harmonic series. So this one converges conditionally, because that's what you call it when it's only converging because it's got the minus signs thrown in. And if it weren't alternating plus minus, it would not have converged. So that's pretty straightforward. And it's kind of cool that absolute sounds like a bigger deal than it is. Absolute convergence is saying, hey, let's pretend that -1 to the n wasn't there. It was all positive signs. Would it still converge? All right, so let's take a crack at a few. All right, so let's find out if it converges absolutely or conditionally, or diverges even, right? Because it doesn't necessarily have to converge at all, even if it's a plus-minus scenario. Well, we've got an alternating series, which means all we have to do is have the limit as n approaches infinity of the formula b0, b0. And for this limit problem, we kind of ignore the -1 to the n, because all that was doing was just creating that plus-minus situation. So let's take the limit of 1 over n to the 1/2, and 1 over square root of n, and obviously this does go to 0, because the square root of infinity is still a really big number, and 1 over a really big number is 0. So these terms are approaching 0 as n approaches infinity, and it's plus-minus, so therefore it converges. The question now is going to be, does it converge absolutely or conditionally? And now we have to apply our usual tests. So the question is, we're now going to test for absolute convergence by ignoring the -1. So if we ignore the -1, we've just got this, which is really a p-series, rewrite it as n to the 1/2. And you'll see that that's a p-series with p equals 1/2. So now you just got to think to yourself, what was that p-series rule? And you remember that, oh yeah, p has to be bigger than 1 to converge. And the way to remember that is the harmonic series is when p equals 1. 1 over n is just 1 over n to the 1, so that's a p-series with p equals 1, and that diverges. And therefore anything bigger than that diverges. So if you do 1 over root n, that pretty obviously also diverges, because 1 over root n is going to diverge, is going to converge even less than the harmonic series did. Well, anyway, so p equals 1/2. By the p-series test, that diverges. So this converges conditionally, because remember, it only diverged if we took the absolute value of everything. That's what we were just doing here with the p-series stuff. We already figured out that because the terms approach 0 and we got a plus-minus, we already know it converges conditionally. The only question was, would it converge? Excuse me. The only question was, would it converge if we took the absolute value of everything? And the answer to that is no. So that's why it converges conditionally. All right, another one, absolute versus conditional. Let's take a stab at it. So let's see. So it is alternating, because we have a -1 to the n plus 1. And remember that plus 1 doesn't really matter. The point is, it's going to go -1, positive 1, -1, positive 1. So it is alternating. We just need to find out if the limit as n approaches infinity of each term is 0. So what's the limit? Oops, why did I do that? n minus 1 over n. What's the limit of n minus 1 over n as n approaches infinity? Well, any way you slice it, L'Hopital's, whatever, that is a limit of 1. So this is a problem for us, because it's alternating, but the terms have to get smaller and smaller and smaller, but they're not. They're approaching 1. So this is going to be one of those ones where it keeps popping up, down, jumping one up, one down, one up, one down, ad infinitum. So this diverges, actually. And when you're diverging, there is no conditional divergence or absolute divergence. If it diverges alternating, it just diverges flat out. It's only if it's alternating and converges as an alternating series that we then further refine the result by saying, hey, is it absolute or conditional convergence? But if you diverge, you diverge. All right, why did I label this one tricky? Could it be because it's not an alternating series? I think that's what's going on, because check this out. This 2 in front of the n really messes things up, because it means that the power of -1 is always positive. Because -1, if we plug in 1 for n, we get a power of 2, and -1 squared is positive 1. If we plug in 2 for n, we get a power of 4. 2 times 2 is 4. -1 to the 4th is also positive 1. So putting that 2 in there means the exponent is always going to be even, and even powers of -1 are always positive. So this is not alternating, it's just your regular harmonic series. So we might as well just cross this out because it's always equal to 1, just throw in a 1. And then right away you can see that this is the harmonic series, so it diverges. And you might wonder, hey, well, what if it was -1 to the 2n plus 1, right? Because now it's always negative. Because -1, this 2n plus 1 is always going to be odd, which means -1 to an odd power is always negative. So this is going to be the negative harmonic series. -1, -1/2, -1/3, -1/4. So you might be wondering, hey, does that diverge? Well, yeah, it does, because there's different ways of looking at it. One is it's pretty obviously going to add up. If the positive version would have added up to positive infinity, then this, therefore, must add up to negative infinity. The other way to do it mathematically is to sort of like factor out the -1. So if you start with -1 over n, which is basically what this was, right? Because we decided that -1 to 2n plus 1 is just always negative, so you might as well just replace it with a -1. What we can do is, since -1 is a constant, we can factor it out. So we'll just put a -1 out front of the summation and make that a positive 1 over n. And now you can see really clearly that I've just got the regular harmonic series times -1. So if the regular harmonic series adds up to infinity, a -1 times that is going to add up to negative infinity. But either way, that's diverging. So whether you've got a 2n as an exponent or a 2n plus 1, meaning everything's always negative, either way, you're going to have a divergent series. The only time it's an alternating series is when you go plus, then minus, then plus, then minus, or vice versa. If it's all negative or all positive, you're not alternating. All right, what's the deal here? I don't know. Let's take a crack at it. So it looks like, what's weird is I've got 2 n's multiplied together downstairs, but couldn't I just combine those? Because there's different powers of the same base. So I could rewrite this as -1 to the n over n to the 3/2, because it's n to the 1/2 times n to the 1, which is n to the 3/2. And now I've got a straight up p series, because I have n raised to a constant power. In this case, the constant power is 3/2. And the deal with p series, once again, is that if p is bigger than 1, then it converges. So first of all, we know it converges because the limit of the terms is 0, because the limit of 1 over n to the 3/2 is 0. And we know this, so we already know it converges because it's a alternating series whose terms are getting smaller and smaller and approaching 0. And now we know it converges absolutely, because even if it was always positive, it would still be a p series that converges. So if we just sort of get rid of the alternating aspect and just take the series from 1 to infinity of 1 over n to the 3/2, that would still, even though it's not alternating anymore, that would still be a p series that converges because p is bigger than 1. This one looks funky. So I've got a -5 raised to the n. So what's the deal here? Well, it looks like it looks like it's alternating, right? Because we do have a negative number raised to a power of n. It's n minus 1, but whatever. The point is we've got a negative sign that's being raised to n minus 1. So it's going to alternate. So that means the only thing that matters is if this thing converges. And that's a little bit trickier. So, well, the limit, actually, this one might even be tough to figure out what the limit of this thing is. So we might just want to go straight to the ratio test. Yeah, let's do the ratio test. It's our favorite anyway, and this has the two telltale signs. I'm going to just rewrite this real quick to make it more obvious what we're doing here. That negative 5 to the n minus 1 kind of makes things confusing. So instead I'm going to do 5 to the n minus 1 times negative 1 to the n minus 1. I'm just going to break out the negative 1 and the 5 so it's like more obvious what's going on. And then n factorial downstairs. So these two things, if you sort of ignore the alternating for a second, these two things are both the telltale signatures of a ratio test candidate, because we've got a number raised to a power of n, and we've got a factorial. And both those are really great for the ratio test. So let's just take this version, the positive version of this thing, and run it through the ratio test. So we've got, if we want to plug in n plus 1, we've got 5 to the n plus 1 minus 1 over n plus 1 factorial divided by 5 to the n minus 1 over n factorial. All right, so now I've got to inverse and multiply. So n plus 1 and minus 1 just go bye-bye, so I've got 5 to the n over n plus 1 factorial, which, as we've seen in the previous video about the ratio test, it's really best to write that as n plus 1 times n factorial. And then this thing, the denominator, I'm just going to invert so I can multiply. That's how you divide fractions. So you get n factorial over 5 to the n minus 1. All right, the n factorials cancel, which is lovely. And then this is a little, it might be not super obvious how to cancel this 5 to the n and the 5 to the n minus 1. But basically n is 1 bigger than n minus 1, right? So you cancel this and that, and you're left with a 5 upstairs. But that doesn't matter so much because constants don't really matter in limit problems. So as n approaches infinity, we just got 5 over n plus 1. The limit of that is 0. So we just found out two things. One is we found out the limit is 0, which is cool. But the ratio, we just did the ratio test, right? And we did the ratio test. We totally ignored the negative 1 to the n. We ignored the alternating aspect of this series. So when we did the ratio test just now, we found out that this thing converges whether or not it's got that negative 1 thing going on. So we just found this thing converges absolutely. So it's kind of interesting that it wasn't super, sorry, I can't spell that word while talking. So we couldn't actually figure out, like even it wasn't super obvious whether this thing, whether the terms even approach 0. So I couldn't even tell off the bat whether it would converge as an alternating series. So the best strategy was just go straight to the ratio test, since it looks like something the ratio test would be good for. And the ratio test told us it converges absolutely. So instead of figuring out it converged as an alternating series first and then doing a test for absolute convergence, instead we went from 0 to 60. We got from having no idea what was going on to going straight to converging absolutely. Pretty sweet. That just shows you how good the ratio test is. That if you've got factorials or you've got exponents of n or both, the ratio test is always the way to go. It makes everything super clear and super easy. That would have been impossible without it. All right, so now we've seen that alternating series are pretty easy to figure out if they converge or not. And we talked about absolute versus conditional convergence. There's one other little vocab thing, remainders or error, which is just always in the part of this alternating series topic. And the basic idea is this. Every series we've looked at the infinite series, right? In calculus, it's not like algebra 2. We're always looking at the infinite series as a total. We never just look at like the first 5 terms, the first 8 terms, or whatever. But for some reason, in this particular section about alternating series, they always feel it's important to mention, well, what if we only looked at the first 3 series, at the first 3 terms, the first 4 terms? How close are we to getting the final sum? Because the whole point is that the terms get smaller and smaller and smaller, right? So if I look on a number line, let's say my final sum of some harmonic series or whatever. I don't know what the sum of the harmonic series is. It might be 1/2, roughly. Anyway, so it's more than half though, because it goes one. Anyway, point is, whatever the sum is, let's just call that S. So first of all, I'm going to get, my first guess is going to be 1, right? So as I add one more term and just keep sort of building up my sum, the terms are getting smaller and smaller. So after one guess, I'm at 1. But then after I add the second term, this minus 1/2, I'm now back at negative 1/2. Sorry, positive 1/2. But then when I add a third, I'm going to the right, and I'm going to overshoot, right, my sum. And 1/2 plus 1/3 is 5/6. But then I'm going to take away a fourth, and that puts me somewhere like right here. But you can see that because this alternating series, the terms are getting smaller and smaller. So what ends up happening is you jump back and forth from one side of the final answer to the next, whatever the sum of the infinite series is. But because you're jumping back and forth and the terms are getting smaller and smaller, you're sort of gradually honing in on that final sum, whatever it's going to end up being. And by the time you're 10 or 20 terms in, you're like really close, right? Down to very few decimal places. So somebody had the bright idea that, you know what? Once I get to like this point, so let's say I had, let's redraw this. So here's the sum. If I started here, or if I start at 0, then I get to 1, then I take away a half, and then I add a third, and then I take away a fourth. So right now my working, having added up terms through 1/4, I'm like, let's say I'm right here. So I still have this error. I'm not right at the sum, right? I'm below what's going to end up being the final sum of the infinite series. But I do know how close I am to the infinite series because when I add the next term, when I add this plus 1/5, I know that that's going to take me to the opposite side of the true sum. Because I'm hopscotching back and forth and I keep leapfrogging over that center value, the actual correct answer, I know that when I jump from this value to this value, I must have crossed the actual true sum of the infinite series, which means that this jump I just made, which was 1/5, is bigger than the distance from where I was to the actual sum. This little leap here is smaller than the leap I just made all the way to the other side of that number. Therefore, if I've added up 4 terms, I must be within this 5th term of the correct answer. Or if I've done 10 of my back and forths, I know that the correct answer must be somewhere between where I am and where I'll be after the 11th jump. So if you want to know the error after 10 terms, it's got to be the 11th term. Or if you've done 25 terms, the furthest you could be away from the true sum of the series is however big the 26th term is. So that's all this is saying, is that the remainder of the series, or it could also be called the error, so that the error after n terms of an alternating series is bigger than 0, because obviously, you can't have a negative error in a way. You're either at the sum or you're not, but you're not going to be like closer than nothing to it. And then the furthest away you could possibly be is whatever the n plus 1 term is. So if you're on the 10th term, the 11th term is the furthest away from the sum you could be. If you're on the 5th term, the 6th term is the furthest away you could be. So when they ask you for the error, or the remainder, after 3 terms, all you have to do is find a sub 4. So the remainder is going to be absolute value, technically, because you don't know if you'll be on the right side or left side. But the remainder is going to be less than or equal to a over 4, to a sub 4, and a sub 4 is just if you plug in 4 to the formula, right? So negative 1 to the 4 minus 1 over e to the 4. So your remainder is at most, we're doing absolute value, so this just kind of goes away, and we get 1 over e to the 4th. So it's super simple, right? They've asked you kind of a weird problem, but it's super easy. You just plug in 1 bigger, a number. And sometimes the way they'll word these problems is they'll say, hey, like use the approximate the sum of this alternating infinite series to 3 decimal places. So all you have to do, or they could ask like how many terms would you have to plug in to get accurate to 3 decimal places. So all you have to do is just start plugging in different n's until you get a term. Like let's say we plugged in the 5th term to our calculator. We did like 1 divided by e to the 5th. All right, so when I do 1 over e to the 5th, I get 0.067, 0.0067. So that means that the error after 4 terms is less than 1/100th. So they could ask me some random question like, hey, well, how many terms do I have to plug and chug through and add together before I'm within 1/100th or 0.01 of the correct sum? And the answer is we just plugged in 1 over e to the 5th and we got 0.0067, meaning the error after 4 terms, which is e to the 5th, which is this 5th one, is less than 0.01, which means we're within 0.01 of the final sum. So the remainder of 4 is less than or equal to that. Therefore, after you've approximated 4 terms, you've got within 0.0067 or within 2 decimals places of the correct answer. All right, find the max error after 4 terms. So on the previous slide, we called it the remainder. On this one, we're calling it the max error. But either way, we're looking at an alternating series, and they said after 4 terms. And pretty much any question they ask about an alternating series that involves not infinity terms, so involves 4 terms, 10 terms, whatever, all we're going to do is just plug in to the remainder formula. So the remainder after the 4 terms is less than or equal to a sub 5. So all we have to do is plug in 5, and we get 1 over 5 factorial, which equals 1 over 5 times 4 times 3 times 2 times 1. So that's 20 times 6. So we get 1 over 120. All right, so pretty straightforward. All right, so that's those remainder problems. But ultimately, alternating series, really simple. If the terms are getting smaller and smaller and smaller and approaching 0, alternating series always converge. And then that whole conditional versus absolute thing is just, hey, if it weren't an alternating series, what would happen? And then this estimated error stuff or remainders, whatever they ask about less than infinity terms, 4 terms, 5 terms, 3 terms, whatever, they're pretty much just always pointing out that, hey, after 5 terms, you're going to be within a to the 6th of your final sum. After 2 terms, so your remainder after 2 terms, the amount you could possibly be off, your error, is going to be less than or equal to whatever the 3rd term is. Because remember, we're doing this hopscotch thing. We're gradually zeroing in on the final sum. So you could never be more than the next term away from that final sum.